A very good morning, friends. So in this video we are going to learn the analysis of a truss bridge Pratt type in Staad Pro using moving load option. So on the screen you can see this is the isometric view or the 3D view of the truss that we are going to analyze Staad Pro. Here you can see the front view. So this Pratt type truss, it has a total 6 panel at the rate of 5 meter center to center. That is the panel length of each panel is 5 meter and the height of the truss is 6 meter. So 6 meter is the height of the truss and the panel length is 5 meter. And here you can see the bottom chord plan. When you see the truss from the top and you see only the bottom chord, so this is the configuration you are going to see. So there are two trusses, truss 1 and then truss 2 parallel to it, and these two trusses, they are connected with each other by beams. These are called as cross beams. And then there is there are more beams which are parallel to the truss between these cross beams, and these beams are called as stringer beams. So the beam which runs parallel to the truss and between the two cross girders, uh, the cross beams is called as a stringer beam. So this is a stringer beam, this is again a stringer beam, this is again a stringer beam, this is also a stringer beam, and these are called as the cross beams. So cross beams are perpendicular to the truss. So how the load transfer takes place? The load transfers from the stringer beam to cross beam and then cross beam to the trusses. So this is a load transfer mechanism in a truss, that the load transfers from you can say the load first comes to the slab of the bridge. From slab it goes to the stringer beam, then from stringer beam the load gets transferred to the cross beam, and then cross beam the load gets transferred to the trusses, and from the trusses the loads are transferred to the support. Okay, and this is the mechanism how a truss works. So now we are going to analyze this in Staad Pro. Okay, we are going to analyze this truss for class A train of vehicle or the class A loading. This loading is given in IRC 6 and the vehicle name is class A. So what this vehicle is? In this vehicle there are many axles and the load of each axle is 2.7 ton. 2.7 ton, 2.7 ton. So you can see total 1, 2, 3, 4, 5, 6, 7, 8. So in this one vehicle, this one whole vehicle, there are 8 axles. Okay, and each axle weighs 27 ton. This 2.7 ton. 2.7 ton or 27 kilonewton. 1 ton equal to 10 kilonewton. So this 2.7 ton will be equal to 27 kilonewton if we are using the kilonewton. Similarly, this is 114 kilonewton. This is 68 kilonewton, 68 kilonewton. This is the axle load. But in actual, if you will see the vehicle, you will find that the vehicle is having 2 tires. So one axle has 2 tires. So this 27 kilonewton load is again divided between 2. So 27 by 2, it is 13.5. So this tire will have 13.5 kilonewton. This tire will have 13.5 kilonewton. Similarly 68. So this will have 34 kilonewton. 34 kilonewton. Okay. So these are the values of axle load. These are the values of axle load and not the tire load. Anyhow, but in this problem we are not going to model this class A train of load as a 2D vehicle. Rather we will model it as only one dimensional vehicle. Okay, how to do it? For that, let's go quick back to the Staad Pro. So here is the Staad Pro. So what I will do is that I will open a new project. I will take the space frame and I will name this as, say, Pratt truss analysis. So the values of the load is meter, is for length, and for force we are using kilonewton. Next, add beam, finish. So when we will finish this, a grid will appear in front of us. But here what we have seen is that our panel length is 5 meter and the height is 6 meter. So we will modify this grid. We'll modify this grid. All these basic steps I have already discussed in previous videos, so I will not discuss in very detail the modeling part. So I will edit the grid. The grid is in XY plane. I will make the distance as 5 meter, and in y direction I will make distance as 6 meter. The number of lines required are 7 lines, sorry, say 6 lines. Okay, and in y direction I need only 1 line. So what I can see is that uh, 30-meter length, that is what I wanted, and 6-meter height. Okay, in y direction the height is 6 meter because spacing is 6 meter. Okay, so you can verify 0 to 6. Okay, so let me change to the front view. Okay, front view. So now I will make this truss. So how to make it? Say click on 0, click on 5, click on 10, click, 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 click. This is over. Say escape. Escape means exited from this command. Again enter this command, then click, 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 click. Okay, again exited and again reactivated from here to here and from to here to here. Okay, similarly from here to here and then here to here. Okay, now again snap mode beam. So you can see the drawing. Okay, this is the drawing. Again and again you need to exit the command and again re-enter it. Okay, so I have made one truss. Let us check whether it matches with this. Okay, see the top. Okay, just a minute. Let me show the dimensions also. I'm unable to, because of this recording icon I'm unable to click that. Okay, okay, close. So 5 5 5 5 5 and 5 5 5 and the height is 6 meter. Okay, let us verify. Okay, 5 5 5 5 5 and height is 6 meter. So okay, perfectly. So our truss is now modeled. We have modeled our truss, right? uh, Next thing is will be to assign properties to this truss. So what properties I am using? So for the sake of easiness and simplicity, I am not using too much sections. I will be using ISA 200 by 25. Okay, 200 by 200 by 25. This is the angle section, equal angle section that I am using for the truss. Truss is a steel bridge. Okay, so let us go to general. First let us provide the support. First go to support, create, pin support, add, create, pin support, fix support. Select all this and only leave FY and click it. So one is pin support and other is roller support that I have created, because in the truss you can see that we are having one is pin support and other is roller support. Okay, so pin support, use cursor to assign, assign. Roller support, use cursor to assign, assign. Okay, so these two supports we have provided. Now let us go to property. Property here in RCC structure we use define, but in steel sections we use the section database. So go to section database, click on it. It will take a few seconds, so have patience. Okay, so in this we can see American sections. We don't need American sections, we need Indian sections. Indians, and then angle section. In angle, just for the sake of easiness and simplicity, I am taking this 200 by 200 by 25. Otherwise you have to choose the sections that that are safe and economical. Okay, so it is a trial based section, and now I am going to assign this section to all the members of the truss. Assigning, use cursor, assign to view. Okay, assign to view and assign. Okay, so I have assigned ISA 200 by 200 by 25 to all the members of the truss, right? Right now, if you will double click on it, it will show as a beam number, but this is a truss. These are the not the beams. So what we are going to do is that we need to convert these beams into truss members. So our truss member is one which carry only either tension or compression, and for that we need to go to specification. We need to go to specification, click on specification, and click uh, beam. Click on beam. Here a new window will open. Click on beam. On beam you will find an option of truss. Click on truss and then add. Okay, so member truss. So what this specification does is that it converts a beam member into a truss. So assign to view. Assign. Okay, now all the beam members have been converted into truss. Although it will show beam number beam, but now it is not a beam, it is a truss member. Now it is a truss member. Okay, so this truss we have created. Now what we want is that we want a truss parallel to it. If you see in 3D, this is a single truss, but in our problem we have a 3D truss. See 3D truss. So one more truss parallel to it at a distance of 4 meter. The spacing of trusses is 4 meter. So two trusses placed parallel to each other at a distance of 4 meter. So what we are going to do? Very simple. Control A, select all. Now we'll use the translational repeat command. So we are going to repeat, and this repetition will be in the Z direction. Z direction by a distance of 4 meter. Right? This is also 4 meter. Okay, and we need to select generation flex all and link steps Okay, Z direction by 4 meter. Okay, so now what I've got is that I've got another truss which is parallel to this truss at a distance of 4 meter, and you find all these points, they have been now connected, they are now linked. Okay, let us go to property. Every member has been assigned property, but these members, they have no property. Let us see from the top. Okay, you see from the top, you find that these are the extra beams created, and these have no property. Otherwise, since we have copied, so all the properties have been copied. Now remember, in this truss, these cross beams, they will behave as beams. Means they will carry bending moment and shear force. Whereas the members of the truss, they are truss member. They will carry only either tension or compression. Okay, so let us go back to our structure. What our structure is. So here we see the plan. Okay, so two trusses are there. There are cross beams. Now stringer beam. There is no stringer beam. So we need to create the stringer beam. Okay, so let's create a stringer beam. So for that, you need to go to add beam option. Here it is. Add beam option. Click add beam. The stringer beam starts from here. So click anywhere on this beam, and when you will wait. It may make a mistake. It may make a mistake. No. And let us see the bridge again in 3D. Okay. So first of all, we need to change the view, and for that see from plus X and select the bottom members. Select the bottom members and select view selected objects only. Okay, we don't want to create stringer beams on the top chord, only bottom chord. So view selected objects only. So the top portion is now hidden, only bottom portion is shown. Now let us see the plan. Okay, so the plan is here. What I have done is that I have hidden the top chord members as well as the verticals and diagonals. Now let us add a stringer beam. So take this add beam option, click anywhere on this cross beam, and he is asking that do you want to add a node here? Yes. So I want to add a node at the midpoint. So select midpoint and then select OK. So it has created a midpoint and started to select to make a beam. Now we'll go to the end cross beam. Okay. What it has done? Okay, it has not done anything. It was just view error. Okay, and again click on the last beam. He's saying, do you want to add a node here? Yes. Where? At a midpoint. Okay, and click OK. So now we have created an additional, we have created the stringer beams. So let us click on the stringer beam. So what I find is that the stringer beam starts from first beam and ends at last beam. Okay, but this is not the case. The stringer beam should be connected to the cross beams also at every intersection. The stringer beam needs to connect it to the cross beams at every intersection. Here it is not connecting. So what we are going to do is that we are going to select these cross beams and stringer beams. Okay, and we are going to use the feature of the Staad Pro. Go to geometry and select intersect selected members. Intersect selected members and say intersect. Okay. So 10 new beams created. So what is done is that now click on this beam. Okay, so now this stringer beams is from this cross beam to this cross beam, and this cross beam is also now broken into two parts. Okay, so all these cross beams have been now broken into separated into two different two different beams, just for modeling purpose. But in actual bridge, it is simply a connection, nothing else. Okay, now let us go and view whole structure. View whole structure. Okay, we will view whole structure. Okay, now one more thing we would like to check here. Go to tools and go to go to select, and then by missing attribute in select, go to by missing attribute, go to missing property. What we see is that these cross beams, the stringer beams and the top laterals, these are not cross beams, these are actually laterals. These do not have any property, so we need to assign property to them. Okay, these top members, these are called as the laterals. These are not the beams, these are the truss members. So we need to assign truss property to these top members. Okay, so select the top members. Okay, and member truss. Okay, otherwise you can go to the specification and you will find the member truss. Okay, view in 3D, then assign to selected beams. Member truss, so member truss assign to selected beams means we want these laterals. Let me slightly rotate it. We want this beam, this beam, this beam, this beam and this beam also to be a truss. So assign to selected members, assign and yes. Okay, so we have assigned truss to these members also. Now these members are also missing the property, so let us assign them property and ISA 200 by 200 by 25. It is showing all the members. No, we need to assign to only the top members. Or you can, what you can do is that you can see the front view, select the top members, again see the 3D view, assign to selected beams, assign and assign. Okay, so this ISA 200 225 is assigned to all the members. Now only stringer beams and cross beams are left. Only stringer beams and cross beams are left. So we need to create a one more section for these stringer beams and cross beams. So okay, let us use the same section right now as of now. So I can again use this to assign to view. Otherwise these stringer beams and cross beam, they have different sections, but let's say for the time being we assign the same. So assign to view, assign and assign. Okay, so assign the same section to all the truss members as well as to the stringer and cross beams also. Clear? So now property has been assigned to each and every member. Now what we need to do, now let us go to load. We need to apply the load. Okay, so go to loads and definition, vehicle definition, we have already done the class definition, vehicle definition, and then click add. Okay, so here we are going to define our moving load, we are going to define our vehicle which will be used for the analysis. And what type of vehicle we are having, let us go and see. Okay, so this is the vehicle we are having. So first axle load is 27, it is 2.7 ton, but in kilonewton it is 27 kilonewton. So 27 114 68. Okay, we need to start from the back. Okay, we will start from the 68. Then 3 meter, 3 meter, 3 meter, 4.3 meter, 1.2 meter, 3.2 meter, 1.2, 1.1 meter. These are the spacing of these axles. Okay. In Staad Pro, the leading load should come at the last. Okay. So here the loads are, as we know, let's start from back. 68, 68, 68, 68, then 114, 114, 27, 27. Okay. Let's add the loads. 68, 68, 68, 68, 114, 114, and 27, and then 27. Okay. The distance is 3 meter, 3 meter, 3 meter, and then 4.3 meter, then 1.2 meter, then 3 meter, then 1.2 meter. Okay. These are the load values. We can check from here. 333, 333, 4.3, 333, 4.3, 1.2, 3, 1.2, 1.2, 3.2, and 1.1. So some change. This is 3.2 and this is 1.1. Okay, 1.1. These are the load values. Let us add the vehicle. Okay, close. So we have add this vehicle. Next is go to load case detail, then add. What we need to add is that load generation. How many loads to be generated? So we are going to generate total 121 loads at an increment of 1.2 meter spacing. So the spacing of the loads will be the increment of load will be 1.2 meter between two load cases, and number of load cases will be generated will be 30 meter total span divided by 0.25 meter, that is increment of load, plus 1. It becomes 121 load. Okay. So number of load cases to be generated 121, and then add. Now click on this load generation, generate load. Here we are going to increment in only x direction. So x increment will be 0.25. Now what is the initial portion of the load? Let us see. So initially 0, 0, 0. Okay. And let us find the coordinate of this point. It is x0, y0, and z2. Okay. And what is the length of the load? The length of the load is 339, 336, 39, 9 and 4.3, 9, 4, 13, 13.3, 13.3 plus 1.2, just a minute, 3, 3, 6, 3, 9, 9 and 4, 13.3, 13.3, 14.5, 14.5 plus 3, 18.5, and 18.8, 18.8 plus 1.1, 19.9. So almost 19.9. Okay, not exact, even if it is approximate, that's okay. So load has to start from the x coordinate 0, z coordinate is 2, and y coordinate is minus 19.8. We'll change if we'll find some difference. Okay, no issue. Add. This is an approximate value. Okay. So this load now I have added. Okay. The load has been added. Y is minus 19.8. It is going. Okay. Sorry. X is minus 19.8. Minus 19.8 and Y is 0. Sorry. Okay. Change. So 19.8 is little more. 19.5. I think it was 5. Change. Or 19.1. 9.2. Change. Okay. That's okay. A little before the bridge, that's okay, no issue with that. Right. So this is the load that we have generated, a class A train of vehicle. The initial portion of the load have been defined and everything is good. Okay. So now we are well on track. Now what we need to do is that we need to analyze this bridge. Just before starting, let us check, and you should always check that members by missing property. So no member by missing property, that's great, means no error will come, otherwise some error will error may come if any member is not having the property. So commands, analysis, perform analysis, all okay, done. Now analyze and run analysis and save. Okay, done. And let's go to the post processing. Done. Okay, no error was there, right? Okay, so here uh, we can see the bridge has been analyzed. Let us start the load. Click on this icon. Again I have to move this panel here because I am unable to reach that. Okay, now so take your cursor to this load case detail. Here it is written 1 load generation. So your cursor should be here. And now if you scroll your cursor, you will see that the load has started to come on the bridge. Okay, you see the load cases are changing. So the thing is that your cursor should be here. If you bring your cursor down and then you just scroll the mouse, then it will not work. So your cursor should be on the this load cases and press Shift V to see the values of the load. And now you can move your cursor. You can see, and now just to exaggerate the deflection diagram, I am using the Control plus scroll so the values are little exaggerated. Okay, scale is high. Okay, so you can see. Let's go back. Okay, so as the vehicle enter, first of all in the beginning, the first string is going to deflect. As the load moves forward, other beams are also getting deflected. Just see, right? Just see the deformed shape of the bridge. Okay, well. So we can see here that our bridge is analyzed. Now we want to see the result. This is a truss. So in truss, the members carry only axial force. The members carry either tension or compression, and we need to find the force in the members. So what we need to do is that, first of all, since we have run the load at the center, and because of this the structure is symmetrical, the values in both the trusses will be same. Okay, so go to results, view value, reactions, global Y, okay, and anode. So we have started the global Y reactions. Okay, now we need to find the force in each member. Okay, the maximum force and the minimum force. So what you can do, how to find the forces? So for that, go to view, and click on structural tooltip option. Click here. Go to beam. In beam, the number should be on, length of, incidence of, property of, release of. And now end forces. When you click on the end forces, there will be starting and ending. Okay, the acceleration should be also off. Now in this end forces starting, of all the forces, only two force should remain ticked, that is Fx and Fx envelope. These two should be on, remaining all off, right? Similarly, in the ending, only Fx and Fx envelope, these two should remain on, rest all off. Change the time. You are having 500, change it to 250. This should be 250, right? And okay. Okay, now if you move the cursor to any member, say I have moved the cursor to here on this member, and here it is envelope. So let us change, not envelope, it should not be envelope, any value other than envelope. Okay, bring your cursor. So when you bring your cursor here, you will find that it is showing the beam number, then the starting end force, then the ending end force, and then there are some values given: negative max, positive max, and force. Okay, so these value you have to write down, that is the negative max and the positive max and force values. So he is saying that it is a top chord member. Top chord member carry compression and bottom chord member carry tension. So what you are finding here is that it is showing that this beam number 73 has a ignore the Fx value, because Fx value will depend on the position of load. As you will change the position of load from here as you will change the position of load, the values of fx will change. Okay, so here now it's 183, so you don't need to take care of that. Just you have to note down the negative max and positive max end forces. Generally they will remain same at the starting and end point. Okay, so to the top chord member, it is showing that the negative max is 0 and positive max is 202.155 kilonewton, and it is coming under a load case of 92. So you can check, you can go to 92 and come here. Okay, so you find that fx is 202.155 and it is again 202.15, so both values are same. Okay, so what this max end forces say, it gives the maximum value, it gives the maximum value of the end forces. So it is a top chord member, it is compression. So in Staad Pro, in the negative max, I am saying only in this negative max, not anywhere else. Plus means compression and minus means tension. Okay, don't apply the same analogy to the below where it is written that ending end force minus 202.155. No, it's not like that. I am saying only about negative max and positive max end forces. In the negative max and positive max end forces, if it is positive, that is compression. If it is negative, it is tension. Okay, so 202.155, it means this is the compressive value. Let's come to bottom chord member. Okay, here. So here what you see is that negative max value is minus 119.938 and positive max value is 0. It means this is having only tension. Minus 119 means tension and positive is 0, it means no compression. Okay, in the top chord member, there is only positive max, no negative max, it means only compression, no tension. But if you will go to any of the diagonals, say this diagonal, not this one, say any other diagonal, let me rotate the bridge. Okay, let me go to this diagonal. Okay, what is showing here? It is showing negative max also and positive max also. It means diagonals carry both tension and compression. The maximum tensile force in this diagonal when this load moves through the bridge is 70.27 and the maximum compressive force will be 51.56. Go to vertical. Okay, in the vertical you will find that the fx maximum value of tension is 39.6, whereas for the compression is 53.984. Right, go to and check this vertical. This will always remain 0. The forces in this vertical will always remain 0. Why these are 0? I will teach in the class. Okay, and you are also seeing the reactions. So you need to write the values of all these forces. You need to write the values of all these forces by taking your cursor there and just mentioning the values. Okay, and one more thing is that you need to find the maximum reactions. So for finding the maximum reactions, for example, I want to find the maximum reaction at this support. So I can just move the load. I can simply move the load. For example, I will start the starting load. Okay, and now I can observe this reactions. This reaction. Let the load start to move 26, 25, 24, 23, 80, 80, 79, 133, 127, 123, 124, 140, 140. Okay, 158, 148, 177. 186, 182. So 182, I think it was the maximum value. Let us move forward. Okay, so maximum reaction at the support is 184.58. Okay, and at this support we want, you need to move the vehicle, you need to cross the vehicle. 150, 180, 189. Okay, I think load cases are over here. Okay, we need to increase the load cases. So instead of 121, you can add say 70-80 more load cases so that the vehicle can cross the whole bridge. The vehicle can cross over the whole bridge. So here there is a small thing that you need to care is that load cases will be not 30, it will be 30 plus 20 meter of the length of bridge. So it should be 50 by 25. So 50 by 54 times 200, 201. So these are 201 load cases. 201. Okay. Come back to here. So you can again edit the load cases. Go to modeling. And then general, load and definitions, then generate load. Here you can say 201, change, it will drop the results. Okay, close, and then uh, analyze, run analysis, save. Okay, again go to post processing mode. Okay, and check. Okay, now see the vehicle, it is moving. Okay, 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 results, let's on the view value, reactions, global Y, anode, anode, close. Okay, so the vehicle is moving. Let's off the deflected diagram. Okay, so observe this one now. Observe this direction. 129, 150, 173, 187, 191. Okay, so this 191 again now shows the maximum value. Okay, okay, no, 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 200, 190, 200. Okay, 200, 147. So we need to see all the axles should pass through the bridge. Okay, so in this way we have analyzed the bridge and how to see the values of the forces. We have also seen, just change some values from the view structure quantity option, change these values. Okay, and just take your cursor on any of the beam, you will find the maximum and minimum values. Okay, so this is end for this video. Thank you very much. We stop here.